Good morning, ladies and gentlemen. Allow me to acknowledge and extend our appreciation to the Dean of Faculty of Geological Engineering, Professor Mega, the Head of International Unit, Dr. Diki, our distinguished guest speakers, Professor Michael from Strasbourg University, Professor Valentin Troll from Uppsala University, Dr. Matias Villarroel from University College Dublin, our lecturers, staff, our students, and all participants, both those attending here and those who are joining us virtually via Zoom. On behalf of the Faculty of Geological Engineering, I'm delighted to welcome to you all to today's international webinar. We are truly honored to have with us distinguished professors who are kindly come to share their expertise with us. Ladies and gentlemen, to commend this event, with due respect to our nation, we kindly ask everyone to stand for the national anthem of Indonesia, Indonesia Raya, and Hymne Universitas Pajajaran. Thank you, ladies and gentlemen. Please be seated. To begin our program, let us hear a welcoming speech from Professor Mega as the Dean of Faculty of Geological Engineering. Professor Mega, the time is yours.
Thank you very much. Good morning, everybody. Especially sorry, I have to read the name. Professor Valentini Troll from Uppsala University, Professor Michael Heap from Starbuck University, and Dr. Matias Villarroel from University College of Dublin. And sorry, I didn't have your name. Thank you very much, and welcome to our university in Pajajaran University in Jatinangor. So hopefully you have pleasant days coming here. To maybe some of you, this is your first time come to Indonesia, especially to Bandung. But Professor Treol, I think you are on many times come to here. You are very welcome, and thank you very much for your coming here today to give some sharing to our student, to our participant here who also attended mostly in Zoom, because as you know, maybe this weekend or last weekend Indonesia was very chaos, yeah. And according to the government, so this week all students should be stay at home and study from home. So we are doing all by online until this weekend. Hopefully, after the evaluation from the government, next week we can start again as regular classes here in the campus. But if they thought there's still some problem with the situation, so maybe students still continue for another weeks online. But hopefully everything will be back to normal within this weekend. So hopefully everybody can have a feel safely like here. Even students are we accepted to go stay at home, but all staff should come to the office just to announce to public that the campus is safe. So especially for the parents, yeah, because they are afraid, how can in this situation our sons coming to the university? Well, some university was bombed by, yeah, so maybe you know the news. So that's why the government decided students just stay at home for make their parents feel better. So, but we staff just showing that university situation campus is okay, no problem. And again, this seminar, thank you very much. Actually, this is maybe is part of a university this Natalis, yeah. So because next 11 of this September, our university become 68th age anniversary, yeah, 68th anniversary. So within this month, we are celebrating any activity in many faculty having such kind of this seminar, something like that. So this your seminar also we put as part of our university anniversary, and also part of our faculty anniversary. Even our faculty university will be on November, yeah. But we already start some activity connecting with this from last July. Yeah. So again, thank you very much for Professor Troll, especially as we already have some our collaboration MOU between us and your university. So this activity is to fulfill this kind of the agreement within us. So hopefully in the future we can have some more discussion to have some more exchange, especially student for exchange, or even we have some like a double degree class, either for PhD class or doctoral class or master class is we can discuss later, or just for exchange student and also exchange lecture, yes, because sometimes university also provide some budget for lecture to go at least for 2 months or something like that to visiting our university partnership to do some research together. So hopefully this is just started for our collaboration with especially your university, and hopefully maybe in the future we can also have some collaborate with Starbuck University and also from College Dublin University. Hopefully we can have some opportunity as well to in the future to have some more collaboration with foreign university, especially from Europe, yeah, Europe country. On behalf of all the staff and student or faculty member, we are welcoming to you, and hopefully you are enjoying your stay with us, and maybe within few days you are going to go some field work. Hopefully maybe I can join some of the field work, I don't know, especially maybe for the Galunggung, yeah, for the Galunggung, so maybe I can join with you. I don't know for the Krakatau, let's see. But this is very interesting as well, because I also haven't visited the Krakatau for the last few years, yeah, so maybe this is also a good opportunity to have some opportunity to the visiting the volcano. Again, and for Pak Diki, thank you very much for organizing all this event, because as his job as head of our international office, yeah, his international office, so it is become his mind test to do some make collaboration with international colleague friend, yeah. And again, for the all participants who are joining in this Zoom meeting, so hopefully you can have opportunity also to have some question or discussion later after the presentation, and take this opportunity to enrich your knowledge based on our expertise guests today morning here. Thank you very much, and Assalamualaikum warahmatullahi wabarakatuh.
Thank you for Professor Mega. And for information, we have audience from many backgrounds. We have from Geology Agency, and then National Research and Innovation Agency, and then teachers from senior high school also, and also student, our master student, and then doctoral student. And for participants in the Zoom, please kindly ensure that you mute your microphone during this session until you are invited to speak, and then you are also encouraged to use the chat box and also for question and comment for during the discussion. We have more than 100 participants join via Zoom meeting. Yes. And to the next agenda, we have begin a main academic session to guide us through the series of presentation and discussion. I'm pleased to hand over the session to our moderator. Today's session will be moderated by Head of International Unit, Dr. Diki. And please welcome Dr. Diki, who will lead us through the keynote talk and question and answer session.
Okay, thank you for the announcement and also the preparation for our program today. I would like to welcome all the speakers from Europe who just arrived 2 days ago, and yesterday they went to Tangkuban Perahu volcano. And also thank you Ibu Dekan Dean for the welcoming speech to us and then opening this program. Ladies and gentlemen, I would like to start the seminar, what we call it as seminar. Actually, in the beginning, we would like to have a very intimate discussion with the students, actually. But things differently approaching yesterday or since last week, actually. So then we shifted the program into like this, into what we call it a seminar, online seminar. But actually, we hope that we can have a good discussion and intimate discussion about the theme that you already prepared for our lecture. In the beginning, when I discussed with Professor Valentin Troll, it was a lecture actually. But then we think that it will be more useful if we can have more audience. So it has been announced that we have, I think, more than 129 in my Zoom platform participants, and it will be more because in the next 10 minutes there will be more students to join into the Zoom after the classroom. Today I would like to invite, I think the first is of course Professor Valentin Troll for the presentation. It's about the volcano hazard and resources, right? I think also Professor Michael Heap, and then Dr. Piero, please come to the stage. I don't know how to prepare your presentation, but anyway, it's just discussion for us. It's just discussion for us, and hopefully that all the things that you brought here to our audience here, and also yesterday I discussed with the head of Volcanological Survey of Indonesia. They also attend our meeting today. Will be very useful for our research, for our students also. And I also inform ITB, Dr. Mirzam, but he is now in UK up to next week. So, but he said he will join also our, Zoom from ITB and from UK for our discussion. But anyway, again, I would like to thank for all of you, and then welcome to our campus in Jatinangor for both of you, maybe. For you, it's already here. And if you enter the gate, you can see the very big banner in that one. We hope that it will encourage students to interact more about the research of volcanology. Because according to our Indonesian Association of Geologists, in Indonesia, though we have 129 active volcanoes and 100 more volcanoes in Indonesia, the researchers of volcanoes are decreasing. So hopefully it can give us a hint, encouragement for our students, for our young people, because now we have about 40 study program of geology in Indonesia. At least we produce geologists every year about 3,000 to 4,000 graduates. Okay, just continue while waiting for the preparation. Okay. I think you should come to the Zoom, right? If you want to present directly from your. Oh, okay. So it's much easier.
But I agree with you because while the number of fatalities from volcanic eruptions is declining, many people think we need to also scale back the research on volcanoes. But the problem is that the fatalities is one difficult aspect of volcanoes, but the costs that are associated with volcanic hazards and volcanic destruction, they are skyrocketing. And they have actually multiplied with factor 10 over the last 20 years.
Oh, two decades. Yeah?
Volcanoes are very expensive. That's the real problem. Small eruptions can cause large devastation. And in our technologically advancing society, we are becoming increasingly vulnerable.
Okay.
So there was this very strong example recently. A little volcano in Africa, Nyiragongo, erupted, and it produced a small lava flow. But the small lava flow was going over a road, and the road was the main road to bring tin ore from the mine to the harbor. Okay. And because they couldn't bring the tin, China suddenly had no tin. So the consequence of a small eruption in Africa had global effects, because China had a shortage of tin supply for its entire industry for a whole week.
Okay.
You can think about the financial costs associated with this. So while fatalities are a problem, the financial costs that even small eruptions are causing are increasing many-fold. And I think this is where volcanologists need to work much harder to help society to not become so vulnerable.
Okay, so it's not only about the eruption actually, but things after the eruption has become the problem.
Absolutely, it's what's often referred to as cascading effects. So there is a small effect at the volcano, but the systems are all connected.
Okay.
The biological system, the human system, the infrastructure, the technological systems. the connections create a ripple effect.
Okay.
And
okay.
so small eruptions can have big problems. Right now in Iceland, we have a similar situation. We have a relatively small eruptions, but the eruptions are migrating closer to the geothermal power plant and to the fishing village of Grindavik. And the problem is that the power plant produces electricity and hot water for the international airport. So whenever the lava goes to the power plant, there's a risk that the airport has no electricity.
No electricity.
And the airport is the main import source or the main import location for food.
Okay.
Because Iceland is not a great agricultural place.
Okay.
So the volcano, although small, may actually limit the import abilities for food supply. And that can have very big consequences.
Yeah.
Although the eruption as a geological phenomenon are comparatively small.
Okay.
So there's a misconception these days that large eruptions cause large damage and small eruptions cause small damage. It's not that trivial anymore. So.
Okay. Wow, wow. You open our mind that the things that not always that small eruption cause small danger, but it
exactly it's not a simple correlation. It's a much more challenging combination. A small eruption in the wrong place can do a lot more damage than a bigger eruptions in the right place.
Okay. Okay, thank you, sir. So I think it opens our eyes, opens our minds also that volcanology is not only for geology actually, but it should be studied by other science, by other stakeholders, not only us from the earth science, because the effect, the cascading, the small amount of volcanic eruption can do something with very big bigger picture there. So then I think as it mentioned and also been informed that our discussion today is has been distributed not only to the geological stakeholder in Indonesia Association, but also to the National Research and Innovation Agency. Some people are there also from Geological Agency also in our case, and then also students, of course, from our faculties. And I think Dr. Aton mentioned that also teachers, senior high school teachers, and also students of senior high school also attend our seminar today. So it's a broad, audience to understand what is happening and why. Just very simple one first, maybe to inform them. What is this? Because sometimes even we in Bandung live near to the volcano like Tangkuban Perahu. Not everybody has been there. Not everybody aware what will happen. Just in our case, maybe in Jatinangor, in our campus here, not everybody understand that Manglayang is a volcano. Yeah, it's a product of volcano here. So we still encourage people to understand about it. But anyway, hopefully that this seminar will be one of our effort, like Professor Mega mentioned as a dean, that awareness to our own, what we can say as stakeholders inside UNPAD, since we have what we call as Dies Natalis anniversary, 68th anniversary for the university, and next November will be for our faculty. So this is one of the program that we explore to them. And thank God, thank you also for you. You can arrive here in Bandung, because I heard that from many colleges in UNPAD, some international collaborators are suspended to come because of the escalation of the situation here in Indonesia. So I was very happy that you are here, and hopefully that you can do your program here in Indonesia. Okay, I think let's go to the main program. Who's going to be the first to present? Okay. Okay. Sorry, because I don't have any notes about your CV. Please explain yourself first. Self-introduction, and then you can further. Okay, yes, please. You can do it.
The gold microphone. So my name's Michael Heap, or Mike Heap, and I am English, although I work at the University of Strasbourg in France. So first of all, thank you very much for the very warm welcome, and it's my pleasure, my honor to present to you today with some of the research that I've been involved with over the last years, which I hope is very relevant for some of the volcanoes also that we will be studying on our visit to Indonesia. So it's to speak to the introduction before, I would be obviously very happy to continue to collaborate with the help of Valentin Troll and with all of you on your very special volcanoes. So thanks for this. It's my first time in Indonesia, and so I've been made very welcome. And so thank you all for your warm welcome. I'm having a great time so far, and I hope to continue exploring and visiting your country, eating your food, which is very delicious. So thank you for all for this. So in my seminar, I'll just explain very simply, very briefly, some of the volcanic hazards, namely the collapse of a volcano and the explosion of a volcano, and how hydrothermal alteration influences those hazards. And so hydrothermal alteration, and if you don't know what that is, I will explain during my talk. This is the main theme of the research that I've been doing in the last years, and that it's the main theme of the research that we'll be doing in the next years, thanks to a grant that together with Valentin Troll that we won last year. So let's see if this works. Wrong way. So a bit of an introduction. When you go to a volcano, the first thing you notice is that it's an amazing, it's a awe-inspiring structure. It's very fantastic. The second thing you notice is what is that strange smell? And the strange smell is the product of hydrothermal alteration. And I would argue that hydrothermal alteration is very, very common at many, many volcanoes worldwide, including the ones in Indonesia. And as a result, if anything is very common or ubiquitous, as I say on the slide, then it demands our attention. If it's always there, then we should be exploring how and why and where it is important. And so here's some action photographs that I've taken over the years. On the left is a picture of me at Volcanic volcano in New Zealand. So there's very active manifestations of hydrothermal alteration. I'm sitting or crouching next to a pool of liquid sulfur. In the middle picture is La Soufrière de Guadeloupe in the Eastern Caribbean, and this is a volcano that I've studied a lot in the last years. And more recently, I went to Costa Rica and I visited Poas volcano, also very hydrothermally altered. You'll notice that I'm wearing a gas mask in each of these pictures, and that's because hydrothermal alteration, as well as turning the rocks from grey or black into vibrant colors like yellow and white, they also emit gases that can be potentially hazardous. And so this is why I'm wearing the gas mask. I'm not wearing a gas mask here because we were in a safe zone. But yeah, yesterday we managed to visit an amazing volcano in Indonesia, and we'll visit another tomorrow. So this is some photographs from yesterday of me enjoying the beautiful manifestations of hydrothermal alteration that we saw. So I mentioned hydrothermal alteration as a common at many volcanoes, but it's also been linked to a variety of volcanic hazards. And so the big ones that I mentioned before are mass wasting, so landslides, collapses, and explosions. And so I'll talk about these, I'll introduce these topics just now. And so in the deposits of collapses on volcanoes, we often see when we put our geology hats on and we go into the field, we often see that in the scar of the collapse that there are altered rocks. And so the photograph of La Sofia de Guadalupe here is, you can see even from this drone photograph that the rocks in the landslide scar are white and they are yellow, and that's because they are altered. And so obviously there's a lot of science that has to be done to prove that that was the reason why the collapse occurred, but alteration is the smoking gun. It's very convenient, or it's very tempting to link the alteration to the collapse, because when we see collapse we often see alteration. And so that's the first hazard. The second hazard is that volcanoes with very well developed hydrothermal systems are also often characterized by erratic explosive events, from small explosions or small eruptions to much larger eruptions, which are obviously less common. Examples of those are on the right-hand side. So this is at Poas in Costa Rica. The little video on the top shows a puff of steam in quite a small explosion at the crater lake, and the picture beneath is a much larger explosion from 2019, which shows the range of different types of explosion that we can have. And so it's very common to have these sorts of explosions at systems with a lot of a well-developed hydrothermal system. So we know that there's a lot of alteration. We can link them with hazards, or we can it's very convenient to link them with hazards because both of those things are in the same place at the same time. But it requires more study. One of the reasons why it requires more study is that it is exceptionally, at the moment, it's exceptionally difficult to predict. And so landslides can occur without so much warning, and explosions can also occur without so much warning. So Valentin was talking about Iceland before. In Iceland, the volcanic activity can be quite different, and the volcanologists in Iceland can very closely track the movement of magma with earthquakes. And so Icelanders also are very good at understanding their volcanic systems, but they have an advantage that they have this ability to track the activity with geophysical signals. But for hydrothermal alteration, the process of hydrothermal alteration does not really make any noise. And these sorts of explosions and collapses often don't have a precursory, telltale precursory signal, at least one that that we've not seen yet. So hopefully with more research we'll be able to better understand these systems and then better predict what's going on. So I mentioned hydrothermal alteration a lot now. What does that actually mean and what does it do? Alteration refers to simply a change. And in this case, we're talking about a change to a rock. And hydrothermal alteration, therefore, means a change that results from the interaction between hot fluids and rock. Hydro meaning water, and thermal meaning hot or temperature. And so what this means in volcanic rocks, this change is typically, if we look inside the rock, it's typically manifest as the dissolution of original minerals, so that the minerals literally dissolve as the rock fluid interactions occur. The replacement of minerals with other minerals, and so, for example, the replacement of volcanic glass with minerals such as clay minerals. The precipitation of secondary minerals, so the hydrothermal fluids often contain a lot of mineral cargo, and when conditions change, such as the pressure and temperature, then this mineral cargo precipitates inside the rock. So that also causes a change which could be characterized or classified as hydrothermal alteration. Obviously, in a volcano, it's very complicated, and we have usually all of the above. So here's some examples of the changes that I was talking about. So the image that you can see is a scanning electron microscope image. So it's an image of the microstructure of a volcanic rock, where black is void space and the grayscale is rock. And so this is an image of a sample from La Soufrière de Guadeloupe, and you can see, hopefully see the outline of a plagioclase crystal, which is very, very unhappy. It's been sitting in a cauldron of hydrothermal activity, and the small black spots that you can see inside the plagioclase is where these fluids have interacted and dissolved and attacked the mineral, which causes the changes. So inside this mineral as well, you can't necessarily see, but you have to take my word for it, that also there's lots of clay minerals inside this mineral as well. And so there's not only has there been dissolution, but there's also been mineral replacement. So that's one type of how alteration manifests itself on this microstructural scale. The other type is mineral precipitation. And what we can see, this is another scanning electron microscope image. What we can see is, if I can try to use the laser pointer, this is a pore that's inside the rock. So remember that the void space is black and grayscale are minerals. And what we can see is that inside this pore, that there are minerals that have precipitated within it. So these minerals are alunite and cristobalite, and don't worry if you don't know what those minerals are. But these are minerals that are precipitated from the hydrothermal fluid into the rock, and this is altering the rock. Alteration is just a change. This is altering the rock. So that was what happens on the microstructural scale. More macroscopically, alteration can be stunning. It can be really beautiful. There's lots of different colors. And so these are some samples from the laboratory. So these are all cylinders from the laboratory. So they're about 40 millimeters in length and 20 millimeters in diameter. So you can see the range of different colors and textures that are produced by this process of hydrothermal alteration. So we have samples here from Costa Rica. These samples are from Copahue in Argentina, Chile. And the ones at the top here, these are from Mount Merapi. And so these are samples that Valentin Troll and I worked on a few years ago. And you can see the different colors and the alterations, different textures. It's very noticeable. So what interests me as a scientist that works in the laboratory looking at physical properties of rocks is what these changes do to the properties of the rock. And so we've talked about alteration is ubiquitous. We've talked about how alteration affects the rock on a microscale, but also on a hand sample scale. But what does that do to the strength of the rock or the permeability of the rock? And these are metrics that are important for understanding the hazards that I mentioned at the start. And so what we have here is we have a sample in the middle. And we're looking at the end members here of this hydrothermal alteration process, where you have dissolution, precipitation, and these processes change the porosity of the rock. So dissolution will increase porosity, and precipitation will decrease porosity. And porosity is very, very much linked to the physical properties that I mentioned before. So if you tell me, as a rock scientist, porosity has decreased, then I will instantly think, well, that will increase the strength and that will decrease the permeability, because that's what porosity does to the rock. Well, low porosity rocks are very strong and high porosity rocks are typically very weak. And so for me, as a material scientist, the process of alteration is changing the properties of the rock, which is really cool. And therefore, it has the capacity or the ability to be able to change the hazard potential of the volcano through the understanding of how alteration is changing the properties. So, for me, changing the strength of a rock could influence the stability of a slope. If your slope is made of weak rock, it's more likely to collapse. If it's made of strong rock, it's less likely to collapse. Also, if you're changing the permeability of a rock through alteration, then you can influence the explosivity or the potential for explosivity of that rock. If you prevent the gases inside a volcano from escaping, then you build the pressure, and this is what causes these erratic explosions. If your rock is very permeable, then the gases can escape. And so permeability is also a metric which is very important for dictating the hazard potential of a volcano. So in this short seminar, we're going to look at 3 examples of how alteration can change a rock, can change the properties of a rock, and therefore change the hazard potential of a volcano. And I do this through an approach of experiments and modeling. So what we'll look at first is we'll look at how alteration can decrease the strength of a rock and how that changes the hazard, how it increases the strength of a rock and how that changes the hazard, and finally, how a permeability change can influence volcanic hazards as well. And we'll go to different volcanoes around the world to explore all those 3 things, so it's a bit of a tour of the world as well that we'll go on. So first, strength decrease. So straight into some data. So we're thinking about how alteration can influence the strength of a rock, and so we have a graph here of uniaxial compressive strength. If you don't know what that is, don't worry, this is just the strength of a rock as measured in the laboratory as a function of the alteration. So the alteration here is defined as the percentage of minerals that shouldn't be there. The percentage of minerals that are the secondary minerals, the new ones, the replacement ones, the ones that are precipitated. So what we can see, each of these little points is an individual rock sample that was measured in the lab. So each point is a small cylinder of rock that was prepared for laboratory experiments, and then we deformed it in the laboratory. So what you can see, hopefully, and there's a bit of scatter, is that as alteration increases, your strength is decreasing. And so it's obviously not perfect, but for an experimental plot, this is quite a convincing data set, or at least to me, this is a convincing data set. So why is alteration decreasing the strength? Well, I gave a clue earlier in the lecture, in the seminar, that the alteration is attacking the rock with these rock fluid interactions which are causing replacement and dissolution of minerals. So this is the picture I showed earlier of this very unhappy plagioclase, which is full of clay, which is typically a very weak material. And so we're changing volcanic glass, which can be very strong, to clay minerals, which can be very weak. That's one reason why the alteration is decreasing the strength. And also, we have this dissolution textures. And so this is increasing the porosity, it's decreasing the strength, and so this is the reason why we have this decrease in strength. So that's on the laboratory scale. So to understand the volcano, we need to go to some modeling. So what we have here are some models. This is two-dimensional models. So this is our volcano here. And we have 4 different scenarios. We have a scenario where the volcano is not very altered, a scenario where the volcano is slightly altered, a scenario which mimics the present day alteration. So this is informed by geophysical measurements, and a future scenario where the alteration is increased on this side of the volcano. So the darker the color, the higher the alteration, the little key that I give in the top of the diagram there. So these are the results of the modeling, these four pictures on the right-hand side, where colors inside the 2D cross-section of the volcano is related to strain rate. So if we see bright colors, it means that the strain rate is very high, which means that the rock is moving down slope, which means that your volcano is unstable. And so what we can see very clearly is that as you increase the extent of the alteration, we increase the movement of the flank of the volcano, and therefore we increase the potential for collapse. And so here I think alteration has definitely decreased the stability of the slope. So in terms of strength increase, I just explained about how strength decrease can reduce the stability of a slope. So maybe an increase in strength through alteration can help the stability of the volcano. Unfortunately, spoiler alert, this is not the case, or it was not the case in this example here. What we see is, again, a very similar diagram that I showed before, but this time we have strength as a function of the porosity of the rock. A lot of the rock samples that were collected in this case study all have about the same strength, apart from these ones here. Again, each symbol is a different sample that was measured in the laboratory. So these ones are a lot stronger than these ones. And what's interesting this time is that those really strong ones were the most altered ones. So it's completely the opposite that we saw last time. So why is this the case? Well, the reason why this is the case, like I demonstrated earlier, that this is, again, it's more scanning electron microscope images. And what we can see that this time alteration is not necessarily dissolving the rock, but it's precipitating minerals within the rock. And so we have microfractures and we have pores, and they are filled with mineral precipitation. And this is strengthening the material, because cracks within a rock, or fractures within a rock, are often used to promote or initiate failure of the rock. And so if you fill it with a mineral, then we can increase the strength of the rock. Which might sound good, but also that mineral precipitation has decreased the permeability of the rock. And so we have here permeability as a function of porosity. It's the same samples as we saw before. These black triangles that were very strong are also very low permeability. And in a lot of different geoscience disciplines, low permeability sets off an alarm bell, because low permeability can create problems with poor fluid pressurization, which can create problems in geotechnical science. It can create problems in hydrology, all these different geoscience disciplines. And unfortunately, it also creates a problem in our volcano as well. So although our rock has higher strength, it has a lower permeability in this case. And so what we did is we made another model where we put the values from the experiments into the model. So we made the alteration zone stronger, but we made it less permeable. And then we saw what happened. And what happens is, as you increase the alteration, you increase the deformation of the volcano. And so the result is very similar to our previous case study, where alteration increased in stability, because we have it here as well. But this is through a different mechanism. by decreasing permeability, we increase pore fluid pressure, which weakens the slope. So as a little summary, we have these two different end-member types of alteration. We have dissolution replacement, and we have precipitation. And in the examples that we looked at, both of those types of alteration can cause problems for the stability of the slope, but by different mechanisms. This one by weakening the rock through precipitation, through dissolution and replacement, and this one through a permeability reduction, which causes pore pressure increase and instability as a result. So in terms of permeability decrease, so that's our third example. So we've looked at what strength decrease through dissolution can do. We've looked at what a strength increase through precipitation could do. But now let's look at what a permeability decrease could do to the hazard potential of a volcano. And we're going to switch from looking at the hazard of flank collapse or slope instability, and we're going to switch to what alteration could do to explosivity, explosion potential. So here are some graphs, one that you've seen before, and then a few other graphs that are either in preparation or published. So we have permeability as a function of porosity in all of these graphs here. I don't have time to go into the details here, but what these all show is that if a rock is altered, it is associated with a low permeability. And so the graph in the middle shows data from rocks from Merapi, in fact. So this is permeability as a function of porosity. All of these data here in the middle are not particularly altered, and they align on the trend that we would expect for fresh rock, unaltered rock. Their porosity permeability is what we would expect. The brown and green points are altered materials, and these have a much lower permeability than their porosity would suggest. The sample here has a porosity of about 20%, but its permeability is many orders of magnitude lower than it should be, and that's because of the alteration. So we can explain that in the same way as we explained the increase in strength. The reason why alteration is reducing their permeability is because the alteration is precipitating in pores and cracks, which are the conduits for fluid flow in these materials. So the fluid would be quite happily flowing down this crack, but because it is partially sealed now with alunite, it reduces the capacity for fluids to move through the rock, reduces the permeability, and this is the reason why alteration is reducing permeability. So let's skip over that. So we'll explore two case studies very quickly now about how alteration can decrease permeability and therefore increase the hazard potential of the volcano. We're going to look specifically at explosions. So the two case studies are how alteration can reduce permeability within a dome, and also how alteration can produce a low permeability hydrothermal seal. So again, the formula is the same. We do experiments in the lab to understand what alteration does, and then we use those values in larger scale models to understand the behavior of the volcano. So this is the main theme of what we've been doing. So in this example, we have a very simple 2D model. This is the lava dome here. We have a magma-filled conduit and an edifice. And what we've done in these simulations, guided by the experiments, we've changed the permeability of the dome. So we've decreased the permeability of this dome in the model, and we're going to understand what that does to the pressurization underneath the dome. So here are the results of the modeling. And so we have three models, one where the dome permeability is quite high, 10 to the minus 11, one where it's in the middle, and one where it's quite low, 10 to the minus 13. So these were informed by the laboratory measurements. And what you can see in the models is the color represents the overpressure, the pore overpressure within the volcano. And so the more white and yellow the color, the higher the pressure underneath the dome, which is creating the problem that I mentioned before. The gas wants to get out, and if it can't get out, it will smash its way out. And so, interestingly, what the modeling showed is that the pore overpressures that generated in our model were sufficient, they're high enough to fragment the rock and the magma. So these models don't simulate fracture and breakage or explosion. They're just showing how the pore pressure increases. But what we can see is that the pore pressure increases high enough for it to be a problem using other experiments. So the last example is, again, how permeability can change through alteration and can cause problems with explosivity. So instead of the alteration of a dome, here we're looking at the formation of a hydrothermal seal beneath the crater lake. So I showed you pictures before of POAS, on video of POAS, where there was explosions in the lake. Underneath the lake, we have a breccia-filled conduit, where we have lots of rock fluid interaction, we have lots of hydrothermal alteration, and this can create a low permeability seal, which can build up the pressure and then be the cause of these explosions. And so, while the volcanological community is reasonably happy with this as a mechanism, we combined experiments and models to be able to show that yes, this is possible, or this is a potential reason behind why we see these explosions. So this is the model set up here, and what we're going to do this time is we're going to decrease the permeability of this hydrothermal seal. Again, the numbers that we use in the models is, I'll be very quick, the numbers that we use in the models is guided by the experiment. So here we see the results of the modeling, and what we can see, the red colors here indicates the pore fluid overpressure. This is the permeability of the hydrothermal seal. As we decrease this permeability, we increase the overpressure underneath, and these overpressures can reach reasonably high pressures. So in this case, up to 6 MPa. Yeah. I'm right at the end. So the overpressures that the model showed us was up to 6 megapascal, but when we look at the tensile strength of the material forming the seal, we see that the tensile strength of the material is all below 6 megapascal. So what we've shown through experiments and modeling is that the permeability reduction is capable of producing an overpressure which is higher than the strength of the rock, which results in, as I put in capitals here, an explosion. So to conclude, as I mentioned at the start, alteration is near ubiquitous at volcanoes. It's very, very common. It changes the rock properties, and by changing the rock properties, it can also change, I hope I've convinced you, it can also change the hazard potential of the volcano, and we did that through experiments and modeling. But there is so much to learn. These are some of the first papers that integrate this synergistic approach, where we have people like me that work in the laboratory, we have people like Matias who works with numerical modeling, and we need to combine our expertise to understand more and more about this process. So the timescales, if you were listening very intently, you noticed that I didn't talk about how quickly alteration can occur, and that's because we still don't yet understand that process. The distribution of alteration, the heterogeneity. So hopefully Daniel is understanding the distribution of alteration right now with the drone. Whether or not we have strengthening or weakening, there's lots of open questions. There's lots more to understand, which is where our new grant comes in. So I mentioned at the start that we had received a new funding from the European Union. So this project is called Rotten Rock, and it involves what I said we needed to understand this process. It involves different people with different expertise. So these are the four principal investigators. Thomas Walter in Berlin, who is an expert in remote sensing. So Daniel is his postdoc now, who's who will drone all the volcanoes that we visit on our trip. Valentin Troll is our resident geochemist. This is me in the lab. I'm the rock physicist. I squash rocks in the laboratory. And then Claire Harnett is who's not with us on this trip, is our modeler. And so she's the supervisor of Mati. And so with all our powers combined, we hope to really understand alteration. And that includes, or it necessitates collaboration with countries with very interesting and exciting volcanoes, which is why we're here, which is why we're discussing with you, why we're collaborating with you, and why we're very excited to be here. Because through studying your volcanoes, we can understand these processes for all the volcanoes that have the same problem worldwide. Can we predict, can we anticipate these sorts of hazardous events at these volcanoes? And thanks very much.
Okay. Thank you, Mike. You can have a seat.
Yes.
After this, okay. I think we'll have three presentations on the consecutive one. So then after that we can discuss. So we still have plenty of time after three presentations. And for the second presentation, I would like to have Professor Troll for volcanology resources. Please.
Thank you very much. Is that okay with this microphone? Can you hear me? Is that okay for Zoom?
I think so.
I hope so. So fantastic. Thank you very much. It's a great pleasure to be back. And thank you for the kind words of introduction. We just learned from Heap about our new project and the volcanic hazards associated with hydrothermal alteration. And I'd like to continue now talking a little bit about what I call the positive sides of volcanoes. Volcanoes have a bad reputation, so people think of volcanoes being, dangerous and destructive. But I have a friend in Spain who always says, there's nothing bad that isn't also good for something. So there's a duality in everything, and like with humans, we have different sides, and not always good, not always bad. And this is the same about volcanoes. So I'd like to bring across another side of volcanoes today, because many people do not fully appreciate what volcanoes actually do for us in terms of good things. So I'd like to talk about this aspect here, and I hope I can get this to work. Let's see. Mike, help me. Where did you press to go forward? Oh, here we go. So here's the bad things. This is Etna, and Etna is actually...
I think there is a comment that it's better to use this one.
Then I will use this one. Thank you very much. So this is Etna. Etna is a big European volcano, and it's been very active, and people are of course very concerned. So this is the bad side of volcanoes, if you will. And oops, I'm going the wrong way. Now it's getting better. And well, you may have heard about the Pompeii eruption of Vesuvius, which wiped out Pompeii and Herculaneum. And so we are worried about volcanoes, and we often associate them with pictures like this from Hawaii and Etna, and now Iceland as well, where lava goes over infrastructure, over roads, destroys houses. And as I mentioned earlier, the economic aspect is actually staggering. we are facing phenomenal costs that come from interaction with volcanoes, where immovable objects, immovable infrastructure is very vulnerable to volcanic eruptions, even very small eruptions. So, and this is a few images from Merapi, where I started my work in Indonesia. This is from 2006, the village of Kaliatem, which was entirely destroyed. So these are the pictures that people, they memorize them and they stick with us. But the volcanic resource aspect is what people don't immediately recollect, and I'd like to talk a little about this. Volcanoes and their underlying magmatic processes are the principal agents of redistributing materials, particularly minerals, within our planet, and therefore they are a key feature in the understanding of the concentration of metals and minerals and fluids, in fact. And this is crucial for us humans living on the surface of the planet. So let's start with some metals here. And Sweden is a big mining country, so we're mining a lot. There is no active volcanoes in Sweden, but we have many old volcanoes. And the old volcanoes are subduction zone volcanoes. So what we have in Sweden is effectively what you have in Indonesia, but only our volcanoes are 2,000 million years older. So there's a little bit of a difference. The good thing is we can go inside the volcanoes more easily and we can extract material from there, and that's what we do. Sweden is the #1 producer for iron in Europe, and also is very high on the list for other metals and silver and gold. And here is some of my students looking at some of the open pit mines in Arctic Sweden that are mined at the moment. And as I said, there is a lot of precious metals. Here is one of those specimens, a fantastic specimen, retrieved from one of the mines with gold, silver and copper in one sample. Quite special. So, and as you know, copper is also very important. Gold is also medically very important, and silver is one of our best electric conductors. So we need all of them. And looking at the projections of how much we need in terms of metals to electrify, for example, the traffic, the projections are mind-blowing. We will need to mine more copper than ever before in human history. And this is something that people don't quite realize. And steel, iron. Steel is going to be, for a long time, the most important metal. There's a lot of talk about critical metals these days, but steel will stay with us. If you think of building bridges, building skyscrapers, everything in these larger construction fields needs steel. Cars still use a lot of steel, so all of this is relevant here. And increasingly we're looking for more exotic metals like manganese and cobalt, because we need it for batteries, and we're now exploring also to get cobalt from more exotic places. If you think about space mining, ask yourself, why is Elon Musk interested in space mining? Well, because there's a lot of cobalt in the asteroid belt, more than anywhere on the planet. There is some on the planet, but it's in the Earth core. And it's a little hard to get there. So this is why space mining is so attractive. And submarine mining as well. So here the rock specimen I show, it's got a crust of manganese and cobalt on a submarine tuff. And this is why people want to go to the bottom of the ocean and extract that material. So, but let's talk a little bit also about the minerals, and I think volcanic minerals have been very important for us for a long, long time. Of course, they're valuable, they're precious, and if you look at the various crown jewels here, so there's the British ones and the old Holy Roman Empire ones, all of them use various minerals, and well, once they're really clean, we call them gems, and they, of course, attract huge amounts in terms of economic value. So we've been valuing them for a long, long time. Many of them originally come from volcanoes, of course, and the most important one that we all treasure so much is diamond. And you can make diamonds by impact from meteorites. That's the only other way apart from volcanoes. And Well, you can't wait for meteorites to make diamonds all the time, so you have to go to volcanic necks like kimberlites. And there is a lot of these beautiful diamonds that come through kimberlite diatremes because they bring up materials from deep inside the earth very rapidly. Diamond is technically unstable, but if you bring it up very rapidly, it doesn't have time to adjust to its surrounding, and then diamond stays a very hard mineral. But it's carbon, so it burns. So you should put your diamond rings away in a, well, fire-safe container if you leave your house, because if there is a fire, your diamonds are gone. So diamonds are not forever, but they are, of course, industrially very important, simply for the reason that they're super hard. So as an abrasion tool, they are vital for human society. And now we make diamonds in the laboratory because it's actually getting cheaper and cheaper to do that. So, but having mentioned minerals that we use, I also want to talk a little bit about stones. Volcanic stones are often underappreciated, and I would like to remind us all that one of the most important tools that humans developed was actually obsidian. So we used obsidian to make cutting tools, and here's various examples from different cultures all around the world. And there is some Mayan arrowheads, and there is some spearheads from New Zealand and from Hawaii, from Polynesia, and particularly cultures that had no access to metals. They were living in a stone age, and these tools are actually very important for human development. And I should add that a lot of surgeons these days, they still use obsidian blades for surgery. And I learned this only a little while ago. The reason for that is that if obsidian breaks, it breaks so sharp that you have a single atom at the cutting edge. And you can't do that with steel. So actually a cut by an obsidian is usually so clean that it heals a lot better. So really professional surgeons, they apparently use obsidian blades. So if the president needs surgery, most likely the governmental doctor that will do the surgery will have a tool like this. So going back to Stone Age methods to do high-tech surgery. And I find this quite impressive. So volcanic stones are very important. And here's a few old examples to support this. Obsidian tools from Turkey, for example, 5th millennium BC. So this was 7,000 years ago. And here's some from the Mayan culture in Central America. They look strangely similar, so I think people had similar ideas, even though they were in very different parts of the world. And I came across this the other day. I was really fascinated by this. This is the oldest mirror that we know of. And it's also 5th century BC, so it's 7,000 years old, and it's polished obsidian, and it still works. So it's fascinating in this context. But having talked about obsidian, I think we have to also talk a little bit about pumice, because we are mining huge amounts of pumice all over the world for the simple reason that we use it as an abrasion tool. And of course we use this in industrial applications. Pumice is a very porous rock. It's got very high porosity. It's also got high silica, making it very hard. And that means it's very glass rich usually. And you can buy pumice powder and for abrasion in large factories, for example. But you also kind of get in contact with a lot of pumice on a daily basis. Many people don't realize that. If you look very carefully here in some of these cosmetical products, if you look at the small print, it says with pumice stone. So you can use your exfoliation product here, and very frequently you actually get in touch with the real pumice. Of course, it's ground down. You would see it only under the microscope, but this is the hard bits that actually exfoliate your skin. Having said this, I should point out that, of course, we use pumice in all sorts of personal hygiene applications, but if you are into whitening toothpaste, you actually will put pumice in your mouth every time you use it, because the tiny little flakes in there are also volcanic pumice. So, having said this, when I was young, these type of jeans came up, the stone-washed jeans. So prior to that, the jeans were always really dark, and then the kind of faded look came out, and as a young man, I thought, oh, I need to have stone-washed jeans. Little did I know that the stonewash actually comes from pumice. So what they do is they put the jeans into a tumble together with the pumice, and then, well, they look worn. These days, I look back and go, it's a bit silly buying worn-out jeans, but, well, fashion is a different thing. So, but an important aspect I like to highlight is what people often refer to as white gold, and that's porcelain, China. And it's often underestimated, but this has been a huge revolution for society, simply because it's a hygienic product. Suddenly, we could actually clean things. There is very little organic growth. Imagine you eat from a wooden plate every day versus a porcelain plate. The wooden plate will, you know, have all sorts of reactions after a while, and this is of course important. You can use this as a sterilizing aspect when you kind of store medical instruments and sort of thing, and this has been revolutionizing the world. The actual major population growth, certainly in the northern hemisphere, actually coincides with the introduction of porcelain. And there's a much bigger aspect here for human society than most people appreciate. So let me talk a little bit about another mineral we're getting. And yesterday we've been at Tangkuban Perahu, and we all have clothes now in our hotel room that smell of sulfur. So here, sulfur is very important. These days, we are producing sulfur as a byproduct from refining petroleum. But this is becoming less fashionable now. And when we stop the petroleum use that we see today, we will have a new problem. And that is, we need sulfur from somewhere. And the best guesses that I understand are out there is that we have to go back to mining volcanic sulfur. And many of you are aware, Kava Ijen, for example, one of the high-profile active sulfur mines in East Java, and the pictures on the left are from there. There, we will likely have to go back to volcanoes and mine more of this. There's an image in the top right here. This is from Chile, from northern Chile. This is a place called Aucanquilchan. It's a high-altitude mine. It's no longer operational right now, and it's above 5,000 meters. And I think these kind of high-altitude mines will come back once we need the sulfur again. Sulfur is not only important to make gunpowder, but sulfur is also very important for disinfection. And well, I'm showing you one of these soaps there, the Shanghai sulfur soap, which is apparently good when you have skin problems. And there are some old matches from Sweden, and if you read very carefully here, it's calling them Vulcan matches. And well, most of the matches and the gunpowder that Sweden or that was used in Northern Europe actually came from Iceland at the time. So, and we may need to think about mining more sulfur in these places, like Iceland, like Chile, like Indonesia, in the decades to come. So, a few words about geothermal power. You all have a good understanding of this because geothermal power is coming more strongly in Indonesia. It goes back to Wairaki power plant in New Zealand, where in the 1950s, the initial construction of a power plant was made. The idea is that you are pumping relatively cold water down to a heat source, and it's converted to steam. There's a volume increase when the conversion happens, and this volume increase can then be utilized to drive turbines or to bring hot steam up and use it for district heating. There's a problem with this, and that is the pipes we use, they clog up after a while, and the image in the bottom right is one of those pipes filled with minerals in there. So we need to replace the pipes quite frequently, but the good news is people have now looked at what's in the pipes, and there's a lot of silver in there. So now we're going back to the old disused pipes and recycling them for the silver. So, but it took us a few decades to realize that. But So there's a lot of things we can do, and now geothermal power plants are actually thinking about creating extra traps for minerals in these systems to concentrate some of the metals, so we could actually extract from there. So then, of course, there's a lot of geothermal power in Indonesia. This is a Chevron plant in Sumatra that I visited a few years ago, and there's more of those springing up. It's, of course, a very clean and very useful energy. So, a few examples here from Iceland. Iceland is very big in geothermal energy. It's so big that people ship ore from India to Iceland to smelter it, and then they ship it back to India, because the energy is so cheap. And this is quite a phenomenon. And then geothermal power plants have a lot of wastewater, and the Icelanders are very clever. So they use the wastewater and they call it a lagoon, and then it's a tourist attraction. So the biggest tourist attraction in Iceland, the Blue Lagoon, is actually the leftover water from the Svartsengi power plant. So you can recycle even that and make a business of it. So, and of course, the volcanic mud from the Blue Lagoon is also very fashionable as a skincare series, and there you can buy it for a lot of money at the Blue Lagoon shop in Iceland. But you can also go to Takuman Prahu and get it there yourself. A few words about other metals and minerals, and here we have lithium. It's up and coming for batteries. These are salars from northern Chile. And there we have these salt lakes, and it's very dry there. This is groundwater that comes to the surface and it evaporates. And the white material there is not snow, it's lithium salts. And they also have a lot of boron, for example, and this is increasingly quarried, and we're using this for batteries. So here's a few impressions from that. There's of course a debate how environmentally friendly that is or not, but that the market is coming up with this huge demand for it. So I think it's going to be very hard to stop mining in those areas, and I think we will see more of this in the decades to come. And of course this is relevant for green technologies, for making batteries, and therefore investment and retrieval of those kind of minerals becomes increasingly important to us. So a few words about stones, and well, people have been living with stones for a long time. Here's some archaeological sites from the Canary Islands, and there we have these caves that have been dug into, and humans used it since the ancient days for shelter, for storage, and also for keeping livestock safe. And here's a particularly famous place there where people have been living high up in the mountains, very safe, very protected. And this is something that, of course, it's not so fashionable these days, but it used to be up to the 1950s, for example, that people were still living in caves in many places, not only in the Canaries, but also in France and in Turkey, etc. So here's one of the caves in the Canaries that has now become a restaurant, and you can go into a cave restaurant. It's very nice on a hot day because it's very cool inside. And these are probably the most famous caves in Cappadocia in Turkey. This is made into pumice-rich tuff, and it's easy to excavate, it's easy to dig into, and therefore people have exploited this obviously for thousands of years. Well, we're not only building with rock, we're also building on rock. And here's just a few examples where strategically important positions were exploited. But all of these examples are actually built on volcanic rocks, on old volcanic necks. So there's examples from France, Austria, Scotland. And this makes a topographic high because of the weathering resistant nature of the rock. And of course, people realized early on this is a useful place to build a fort or a castle. But not only European phenomenon, of course, this has been exploited all over the world. Here are a few Indonesian examples. So we have Borobudur and Prambanan here in central Java, just as examples. Borobudur, as you know, it's the largest Buddhist temple ever discovered, and it's built entirely of massive volcanic stone. And it's entirely made of andesite or basaltic andesite, and this is quite an achievement. So volcanic stone has been instrumental. It's all come from this volcano here, Merapi volcano, and of course people were very skilled with producing these well over 1,000 years ago. So the Romans have done that as well. The Romans have gone even a step further. They developed the first cement from volcanic minerals. There is very reactive secondary minerals, hydrothermal minerals that Mike talked about. There is zeolites and clays, and if you mix them with water, they actually start to bind. They start to make a cement. And when you look at buildings like this, the Pantheon or so in Rome, standing for 2,000 years. And it's all going back to the volcanic trickery that people have been developed with those materials. So here's a few more examples, a few buildings. This is a church on Tenerife made entirely of volcanic stone. And this is me trying to find the quarry where it all came from 400 years ago. And I think we found the quarry, but the stone is still used today widely. So it's a very popular stone, but the quarry is not in the same place anymore. So here are a few more examples. This is a large church in Clermont-Ferrand in France, also a volcanic region, and like Borobudur, it's built of massive volcanic rock. So people have also used volcanic stone for quite some time to actually use, well, to grind down food. And here, for instance, we have these millstones. It's a bit of a tricky thing. You have to find the right rock. If you have the wrong rock, your teeth will degrade because too many particles come off. And I talked to a friend in Mexico, and he says people still make those millstones there, but it's a family secret to which quarry you go and which stone you take, because the teeth of your entire family depend on it. So, and you don't tell the neighbor where your stone is from. So there's quite a science to this as well. So, and of course we use stone every day. It's non-reactive with most kitchen acids, for example. So many people have stone at home in their kitchens. And of course you can choose varieties, but when you look at the bottom right, there is mainly igneous rocks, mainly volcanic rocks that we use for this. So the biggest use of volcanic stone, however, is as aggregates. We are all using vast amounts of aggregates, more than anything else. And aggregates are crucial for building, and we use them to add to tarmac, we use them to add to concrete. And the upper image there is from Merapi as well. Sand mining close high up on the slopes of Merapi, and this is of course also used for agriculture. When I first went there, I was really kind of a little disturbed about the mining practices there for sand mining. It looked very irregular, let's call it that, and I was really wondering why they're doing it this way. But of course there's a reason for this, and that is, this is likely a channel for another eruption in the future. And if you quarry it this way, you actually create a topography, and that becomes a sediment trap. So it slows down the next pyroclastic flow. So not only are you getting sand for your building endeavors and for agriculture, you're actually preventing the impact of the next eruption. It took me a few years to get to this. It was quite a clever realization, I thought. So people are really helping this. So I want to say a few words about agriculture now, and we talked about lapilli and pumice. And we talk about housing, concrete supplements, abrasives, but the agricultural aspect is also very important. And in Europe, we love to grow wine on those soils from volcanoes. Here's wine from Etna or from France. And well, in Indonesia, it's a little different. There is a lot more sun, and there's a lot more water, and a lot more volcanoes, so you can grow even more exotic things. So here, this is Merapi again, and you see the fertile landscape with the rice paddies, and high up on the slopes, there is more cultivation of other products. And, well, I think what you need for that is water, so this is a picture of an afternoon rainstorm at Merapi. And, well, we know that Indonesia is very famous for all the spices, and this is something we can't really do in Europe. And I'm particularly fond of the Krakatoa pepper that we're showing here in the top right. So, as many people know, coffee is also largely grown on volcanic soil. Actually, 70% of all coffee is grown on volcanoes, and if you have a cup of coffee, you're actually touching volcano every day. So this is a map of coffee consumption all over the world, and the darker the color, the more coffee is drunk. And in Sweden, where I live, we drink a lot of coffee. But we can't grow coffee, so we rely on places in different parts of the world. And it's noteworthy, apart from Brazil, all the countries high up in the north, they like coffee. So I think if you have no sun, you drink more coffee. And, well, we will see about that. Therefore, we're very grateful for volcanoes in other parts of the world helping us to make the best coffee. So here's a few impressions, again from Java. This is from Ijen, and there in the caldera of Ijen there is the coffee plantation, and it makes very nice coffee, and there's a few impressions of it. So I didn't have much of an idea when I came here first, but I learned a lot about coffee when I worked here. So there's coffee beans, and of course they're white at the beginning, then you dry them, and then you roast them, and then you grind them, and then you have a really good cup of coffee. But not only coffee is grown here. I came across this wonderful plantation of cocoa beans at Merapi as well. So now they're making chocolate at Merapi, so you can have coffee and chocolate, and all of it is volcanic. So, and this is not only true for Indonesia. Here's a few examples from Hawaii. So here people are growing volcano nuts, like macadamia nuts, and this is of course also added to the fruits that are produced there. Dole is one of the major producers of pineapples, for example, and they grow, of course, to beautiful sizes in Hawaii. And in the small print there at the bottom of that slide, let's see, I have it bigger here, it is acknowledged that they only grow that well because of the volcanic soil. So Dole, the company, is very much aware of this, and they are trying to buy more land on Hawaii to utilize the volcanic soil there. So, and that's me enjoying the juice. And I think I gave you a good impression of this, and I'd like to close here. And I say thank you for your attention. And next time there's a volcanic catastrophe, try to think of the good things volcanoes do, because nothing is ever only bad, and nothing is ever only good. Thank you for your attention.
Okay, thank you, Fab, for a very comprehensive explanation. I think also some students in our Zoom platform, first time to hear that many products of the volcano actually in touch with us in almost everyday's life. Yeah. So this is a good, let's say, a wake-up call for them, actually, for the new geologists in the future, that our life will also connect directly to the volcano. It's not only about the hazard, but also that resources that you have explained. Okay, the next presentation, I think it's better to be in the 3 presentations in a row. Dr. Matias Villarroel from UCD. Please, welcome.
Yes.
Hello, can you hear me? Yes, there you go. Okay, thank you for having me here. Thank you for having us. Really appreciate this. So I'm gonna change the topic a little bit. We're gonna explore maybe the bad side of the volcanoes. These are catastrophic eruptions, the so-called supervolcanoes. So collapsed calderas. Yes, I'm Matias. I'm a postdoctoral researcher at University College Dublin. I'm from Chile originally, and I've been working at Dublin for 6 months, more or less. And when I arrived there, Chile there's a lot of volcanoes. In Dublin, there's no volcano, so people start worrying. Oh, there's a volcano here? No, no, no. I went there because there is the possibility to come to places like this, where there is beautiful volcanoes and very interesting also. So let's start with a presentation. We're gonna go through a lot of topics about calderas, and I'm very lucky, because Mike already presented a lot of the concepts that I'm gonna go through, so I'm not gonna have to explain them again. And as Mike, I also squash rocks, but in the computer. So if something bad happens, nobody gets hurt, right? Only the one that is giving the money to buy the computers, maybe. So let's start this. Just a presentation roadmap. We're gonna do a little introduction about the caldera, so definition, type, sizes, etc. Then we're gonna arrive to the problem. So when and where the ring faults are nucleated. So in order to have a caldera, we need to have faults, and they are usually called ring faults because they are annular or circular in most of the cases. They can be elliptical as well. And we also going to address some different methods or methodologies that gives us insights in this problem about the mechanics of the caldera, how the fracture form, nucleates, and then propagates, and then we can have a caldera. And then we're gonna finish with some conclusion. Yeah, first, a caldera is a morphological feature. So it's a surface expression of the disruption of the underlying magma system, which is withdrawn of the magma, and then there's a instability on the block, on the roof block, on the upper part, and then that block slide downward. Yeah, and this deformation happens, or it's accommodated by caldera faults, so ring faults. They can be several kilometers in diameter, and they can form either in effusive eruption, but also in very explosive, catastrophic eruptions. So yeah, the caldera forming eruptions, those are the catastrophic ones, the explosive ones. It's very violent phenomena in Earth's surface and represent a societal hazard. But there's a good side of caldera also, because the post-collapse systems provide all the ingredients to have also energy resources and ore resources as well, because there's heat, there is permeability and fluids. So the post-collapse history, it's a good history for calderas. Just an example and for visualization as how collapse process it's developed. Here is the case of Kilauea. In 2018, the volcanic summit collapsed. This collapse started with the drainage of the magma chamber inside. Let's see if I can run the video. Oh, no, I cannot run the video. Maybe like this. Maybe there. Yes, because this is a beautiful, beautiful collapse, and you are going to see the magnitude and everything. So it started with the drainage of the magma chamber, then a little explosive eruption, and then the caldera starts collapsing. A big collapse you can see, and this lasted for a few months. And the effusive eruption happens very far away, so 40, 50 kilometers away, effusive eruption, lava flowing in a vent away from the caldera, but the drainage of the magma chamber induce or drive this kind of collapse. Okay, so this is yeah, a non-explosive collapse type of a caldera process. Then on the other side of the spectrum, we have the explosive one. So this is the very dangerous one. This is the example of the Mount Pinatubo in 1991, explosive eruption. It was big eruptions, almost or around 1,000 fatalities from this eruption, and also disturbed the global weather for about 3 years after the eruption, and created a relatively small caldera, 2.5 kilometers in diameter. But the consequences were big. This is just a sketch of general difference between the mafic calderas, which can be seen as the effusive ones, and the felsic ones, which are the explosive, very dangerous one. The mafic calderas are usually a smaller caldera with not large displacement. They occur by a feeder dike feeding an eruption far away. And on the other side, the felsic calderas are big explosive eruption. The eruption happened within the caldera, and the displacement it's quite large. This is the classic classification by morphology, and just looking at the morphology of the caldera, it's a way to interpret what the magma system might look like. So there's a plate or piston type calderas, which is a coherent block that is going downward. There's the piecemeal, so there are various blocks going downward. Then there's the trapdoor caldera, which is the anasymmetric caldera. It's only going downward one side. Then the downsag one, which is not a lot of displacement in the roof. And then there's the funnel, which is a very deep caldera. And this has been used to kind of interpret what the geometry of the magma system might look like. And then sizes of calderas. So Toba right there is the big one, elongated. It's 100 kilometers in the long axis. It's parallel to the Great Sumatra Fault. And there, on the other side, there is little calderas, but you see what are the consequences, even for little calderas as the Pinatubo that we have there, 2.5 kilometers. And there is a big range of sizes, and also, as you can see in map view, the geometry of the calderas, and so the geometry of the faults that control the collapse. There are also calderas outside Earth. So this is the biggest volcano in the solar system, the Olympus Mons on Mars. And there, on the top of the volcano, on the summit, there is a nice system of nested calderas that you can see very well, some of this annular ring faults. And just the vertical lip of the caldera wall is 3 kilometers inside, so it's very big, yes, very big example. Just a small one. Yeah. And post-activity in caldera may result in resurgence, creating a resurgent dome. This is not a lava dome, as we know. It's made of the material that it's deposited inside the caldera, so intra-caldera, the ignimbrites mostly, and this is because of the residual magma and heat that it's swell up or uplift the middle part or the central part of the caldera. And here we have two examples. Toba is one of the examples also. It has a huge resurgence here, and so looking inside from the caldera to the center, we're gonna see mountains, right? Which are the products of the of the eruption. So this is Cerro Galán on the left side, and on the right we have La Pacana, which is also a big caldera, 65 kilometers in the long axis, and it is a trapdoor caldera. It's has more displacement on the southern side. So the same, looking inside the caldera, looking far away, we can see the resurgent dome, and this dome has a lot of extra structures also due to this uplift because of the residual heat. So we arrived to the problem, what we are gonna address in this talk. So how do we know what is happening inside at depth? So what is the underlying structure of the caldera, and under what conditions do caldera form? So as I said earlier, to have a caldera, we need to have faults. That's the first thing. If there's no faults, that's just a crater, an explosion crater. Yeah, and so, but we don't actually know how they look, because one of the problem is that they are not always well exposed. They are covered by the material of the explosion, and also they are eroded, so the topographical boundary is not the same as the structural boundary. So that's two of the problems in understanding what is the actual architecture in the caldera fault. And the other problem that maybe is not a problem is that the caldera eruptions are not as frequent, right? Which is a good thing, because as you saw, they can be very catastrophic, right? But so we don't have many examples and many data, but there are some recent collapses where we can draw some data from. So first, caldera faults are deep slip, normal or reverse faults. They have some components of oblique slip, and it's unclear if the caldera fault nucleates at depth because of shear forces or at the surface because of tensile stresses. And that's what we're going to see now. And first, pressure conditions. So this is the driving mechanism for calderas. These are pressure conditions within the reservoir, within the magma system. So there are two mechanisms to form a caldera. Both mechanisms starts in the same way. So there is a magma injection, and the pressure within the magma chamber increase, and then they split both mechanisms. So the first one, we can say it's the under pressure scenario. In the under pressure scenario, a feeder dike is feeding eruption far away, and so the magma is being withdrawn from the reservoir. That causes the roof to lose stability and then starts collapsing. And then the other scenario, it's the overpressure scenario, where the pressure inside the magma chamber keeps increasing until the caldera faults form, and then the eruption is imminent. So this kind of process can be mathematically simulated by this kind of analytical solution, and with the use of this analytical solution, we know that in a simplest way, caldera collapse depends or is controlled by the geometry of the roof, so the diameter and the altitude of the roof block, and also the pressure within the magma chamber and the friction along the faults. So it starts with some volume of the magma, it's withdrawn from the chamber, and that weakens the support, exceeding the frictional stability of the fault, and when at some point it's going to collapse. So this kind of analytical solution let us know what are the pressure conditions, so the under pressure value or threshold, so the caldera can go down. Yeah, but most of these models consider very simple scenarios, so isotropic crust, no regional stresses, and also single magma chamber. We're going to see some kind of more complex scenario in the next slides. So this is the structural architecture of the collapsed caldera. So it has 3 stages. The first stage is elastic phase, where there is only a little of subsidence in the surface, and the caldera fault starts growing from the bottom to upwards. Then the second phase is the development, so the fractures reach the surface, and there is the development of a reverse fault. And in the latest of the stages, there is no normal fault. So this is the classical architecture of caldera volcanoes. And how do we know this? Well, by combining or integrating a few methods that I'm going to talk now. We already saw the analytical solution, so let's go with the scale physical model. So these are SAN model where all the parameters are scaled, so they are conducted in the laboratory, but they represent process in the lithosphere. And this is kind of the workflow. There's some model set up, there's some results, and then those get compared with the real cases. So this is an example. There's the scaling here. 1 centimeter represent 1 kilometer on nature, and this scaling parameter lets you know what the material you're using should be, so it can represent the real thing. So I don't know if I can play the video again. Oh, no. Sorry. There you go. So this is one example. The caldera, it's forming. Briefly, you can see that it formed kind of a nested caldera, one inside, one outside. Those are the faults, right? The reverse fault inside, the normal faults outside. And then this is over-trussed by regional structure. So this is just one example of interaction between compressive tectonic and caldera formation. And this is one of the results. They can be processed, these pictures, they can be processed in correlation software, correlation pictures tools. So we can computate or we can know what are the vectors, so where the particles are moving, and also the strain. Mike already talked about the strain, the deformation, how this is occurring, and also we can have some kind of 3D idea of the process by cutting the sandbox, the modeling device. Yeah, and so we can see on the right-hand side of the caldera in the cross-section, the caldera faults are not intervened by the tectonic structures, but on the left side of the caldera, it's been overposing a compressional structure. So the actual caldera fault, it's being reactivated by the compressional tectonic. And structures like this exist in nature. So this is one example of northern calderas, Eocene calderas. So they are exhumed calderas, and there are also thrust fault systems that over-thrust those calderas and kind of modify the architecture of the caldera. So the Cretaceous lava are overlying the intracaldera ignimbrite from the Eocene, so modifying what is the geometric expression of the caldera. These are eroded calderas, so they are not subside as you might think. They have been uplifted, so in the field they look like this. It's just the intracaldera ignimbrites. And then coming to the FEM models, okay? Coming to the FEM models, this is mechanical conditions for the nucleation of caldera faults, and there are three conditions that needs to be met simultaneously for a caldera fault to nucleate. So I'm gonna go quickly with this. So we are looking for this kind of configuration. This is stress distribution, okay? And the idea here with the FEM models, which are numerical models, is to simulate the geometric arrangement of the caldera system and see what geometries are able to nucleate a caldera fault. If they meet these three conditions, these three mechanical conditions. So these are one of the results. I'm not gonna go in detail with this, but we test a lot of different models, and the final result is the most geometries and pressure conditions do not create the conditions for ringfold nucleation, and when they do, they are usually shallow magma chamber, under pressurized, in extensive conditions, and also stacked magma chamber. And this correlates to kind of the seal column model instead of the standard model of magma chamber, which is one seal-like magma chamber. Notice there is the reconciliation of the model that we can have stacked magma chamber, so the actual caldera eruption is feeding from or is tapping from multiple reservoirs that are stacked. Coming to DEM models, and when I say DEM models, I don't mean digital elevation models, but distinct element method models, which is different from FEM because FEM is a continuum approach. This is a discrete approach. So the difference is here that we can model fracture nucleation and we can model fracture propagation. So we can model faults, yeah? And in this case, the magma chamber is that void that you can see there, and it's exerted with a boundary condition on the top wall, so it's under pressure. Yeah, so that's gonna drive the caldera to collapse and also to generate some kind of architecture. And here it is addressed two factors that comes from soil mechanics, which is the regional stress by the earth pressure coefficient and also the reduced density by a pore pressure. I'm not gonna go into detail with this, but this let us try different scenarios for regional. So isotropic, there is no regional stress. In compression, we're gonna have some kind of a squishing of the system, and in extension, we are extending the cross. And then we can have also pore fluid pressure, yeah, that it's gonna weaken the rock also. So these are some of the results. At the right, we have the evolution of stresses. At the middle, we have the strain and also the fracture. So the fracture architecture is it's kind of simple to see. And also we have a graph of surface subsidence and also under pressure. This is for isotropic conditions. Next, we're going to see for extension, for isotropic, and for compression. And what these graphs are telling us is that in extension, you need far less under pressure for a collapse to occur, for the faults to nucleate and reach the surface, and then for the piston to come down, than for compression. Yeah, so calderas, if your caldera is in an extensional setting, it's more likely to generate a caldera forming eruption. And here is the comparison of the architecture of the different scenarios. And you can see some in the extension, there is some normal faults. In the compression, there are reverse faults. So the architecture vary controlled by the regional stresses, but also because of the crustal conditions of fluid pressure. Yes, and this is because both extension and fluid pressure reduce the friction along the fault, so it can go down easier or earlier. These are the applications. So this architecture we can see in nature in recent collapse. The earthquake epicenter, epicenter highlight the pattern or the structural architecture, and they are similar as the modeled in the DEM models. And also the entire sequence of events of earthquake also correlate to the stages of collapse, where there is an elastic response first, then there is an onset when the caldera faults generate, and there is full collapse. And this is one of the examples in Bardarbunga. And the architecture, so it has vertical faults and also reverse faults as this. And I'm going to finish with this. This is collapse phases. So coming back to the Kilauea example, also we can relate this to the models previously shown. The first phase of this eruption is the elastic response, not too many earthquake. In the lower part, you have the earthquake there. Then there is a transition between the elastic phase and inelastic deformation. So we are generated or nucleating and propagating faults through the crust. And at the end, we have a lot of earthquake. That's ultimate failure, and the collapse already happened. This is 500 meters in collapse that happens in 2018. So just to wrap up, this is some new models, 3D models, those that I showed earlier. They are 2D. These are very computationally heavy, so they are very slow to run. You can be waiting one whole week just for every computation cycle to run. But we have some results in that where you can see the 3D architecture in the same way we saw the 2D one. So same, reversed fault at the beginning, then it nucleates another set of faults. And you can see in the final structure, they are colored by the pressure change in the magma chamber. So the first structures that are formed are this outward dipping reverse fault, and at the latest stage it formed this normal inward dipping reverse fault. So this is kind of the architecture. This is in isotropic, but it correlates also with the 2D models and also with the natural cases. Yeah, so just some conclusions, and I'm just going to finish saying that it's important to integrate this kind of modeling approach just to forecasting this low probability but high consequence event. Thank you very much.
Okay, thank you. Oh, very interesting. Since in our discussion in our faculty, we sometimes segregate or disaggregate between the materials, the volcanism, and also engineering. You mentioned about the